Good afternoon, and welcome to this colloquium. I'm Alfio Quanteroni, and I'm the great pleasure and privilege to introduce our speaker today, is Professor Sauro Succi. Sauro got his laurea degree in nuclear engineering from Bologna. At the time, it was one of the very few places in Italy, very outstanding places where to get this type of laurea. And then he continued with EPFL for a PhD in plasma physics. Then he was with EXEC. EXEC at that time was scientific center for IBM, and I had the honor to collaborate with EXEC with many different people working at that time, very outstanding people. It was a very great place for science. And then he joined the IAC, is a CNR Institute, Mauro Piccone, also another very famous institution in Rome, and more recently he is with the IIT, which is the Italian Institute of Technology in Rome. Professor Succi is also affiliated with the two prestigious universities. One is Harvard, the other is UCL in London. He is very well known worldwide for his contribution to kinetic theory, quantum fluids, and turbulent fluids, and particularly is one of the brilliant mind behind the development of the Lattice Boltzmann model, which consists basically of replacing the Navier-Stokes equations with the Boltzmann equations to study fluid dynamics. He is member of the American Physical Society and the Academia Europea, which is the most prestigious academy in Europe. And he got very important prizes, the Humboldt Prize, the Alder Prize from SECAM, the Raman Prize from the American Physical Society. And it's a great pleasure to have him here today. And he will talk on one of his most recent interests, which is quantum computer for fluids. Sauro has also written a couple of books, and I have to say that it was a pleasure to read those books. He has the great merit to write deep things in a very clear way and a rigorous way. And I'm sure you will appreciate his talk today. Sauro, thank you very much for coming.
Thank you, Alfio. Can you hear me? Thank you. I'm blushing having such a great introduction from great scientists like Alfio. So after I blush, I will start with my talk today. So can you hear me well? I think so. Actually, the first thing I should say is that I should have changed this title into quantum computing for fluids, which looks like reassuring. On something more actually reflecting the state of the art, at least for what I am concerned, is are classical fluids quantum computable at all? Because frankly speaking, and I would like to put that in a positive perspective, but I think the question is that this sounds like you can do it better or in a good way or in a less good way, but it to me is still completely open whether you can quantum compute. And I want to make this quite clear, especially to the young people in the audience. Second thing, I should credit Claudio Sanario, who is a postdoc, who is basically doing the hard part of the work, even though I must confess that for this specific topic, which I knew nothing about till last year, I did some homework myself. For a period, I was my own postdoc, so to say, because there is need to go into the details. You cannot escape the details in this subject. Okay, with this premise, first, the topic is still rather exotic. So I think it's a good policy that I explain what quantum computing in general is, although, of course, I will not go into details, but give you some basic guideline before I start, in fact, talking about quantum computing for fluids, which is a specific topic on its own, and it's, I would say, still a sideline of quantum computing in general. So first, quantum computing in general, and then the specifics of the quantum computing. Now, you may or may not know that, at least historically, although there were people before Feynman, but For the record, it was a paper by Feynman in 1982, where he is basically famously proclaimed, and I think this is by far Feynman's most cited paper, okay? Where he said, look, guys, physics, we know it's quantum, so if you want to simulate physical system, you better use quantum computers. And he admitted that it was not an easy job, but that he was strongly advocating that you use quantum computer to simulate physics. Now, a little bit of a recap. This is the plane, if you wish, of the computers versus physics, computers on the vertical line and physics. And what we do 99% today is classical computer for classical physics, okay? Suppose you have this plane, we have 4 quadrants, classical computers for classical physics, classical computer for quantum physics, quantum computer for classical physics, and QQ, quantum for quantum. I don't think I need to ask question. Where we are today is basically digital computers where we use bits, yes or no, 0, 1, nothing in between, tertium non datum, to say with the Latins. And it is definitely true, although I'm basically a CC guy and so is Art. We do mostly classical physics and classical computer. I know a little bit of people who do, for instance, quantum chemistry or quantum physics, and they still use classical computers because that's what we have. And it is true that in some cases you really meet with kind of artificial barriers. When you want to compute a many-body Schrödinger, because you want to solve the Schrödinger equation for any reasonable molecule, you are facing with 100 or 1,000-dimensional state space. And we all know that you cannot use finite difference of the standard discretization method in more than, I think, 4D is the crossover for Monte Carlo, right? So this sector looks like our mathematics, our computational mathematics, isn't really the right tool to face with this problem. There is something in nature with exponential value. And so basically, he didn't write that, but that's my own interpretation of what Feynman meant, is that you should make the transition from CQ to QQ, okay? If you have quantum problems and you formulate the quantum problems in a quantum hardware, then all of a sudden, the exponential barrier is still there. But a quantum computer has an exponential size of the state space. So the two somehow are in balance. Whereas if you insist on working on bits, there is a total imbalance between the computational complexity and your art. So I think Feynman was basically advocating this transition. And there is no mention of this. QC, nobody does QC. There is now a little stream in quantum computers where people are interested in understanding whether the power of quantum computers can be used for nonlinear PDE. But there is really little work, and frankly speaking, even less concrete results. So today, we will be dealing with this quantum for classical system. But before we go into that, of course, a few, well, I can use this. So I don't know, some of you might be acquainted with quantum mechanics. Let's take a crash course. As you know, in quantum mechanics, we deal with the wave function. The wave function is generally a complex scalar, okay? So real, two real fields, a real and imaginary part. And it is typically expressed, as you know, as a sum over a specific basis function. Okay, it could be, you know, Hermite polynomials, Legendre, Laguerre, a set of a complete basis in Hilbert space, which is infinite dimension. And this is just a matter of notation, and these coefficients are complex. And the meaning of this wave function is that if you square it, okay, the resulting P is the probability of finding a particle around position X time T. So quantum theory is a probabilistic theory, and you replace deterministic trajectories with probability. I better read it from there because I have light scattering. So now the point is that if this is the probability and you integrate all over the space, you must end up with 1 because the particle must be. And if you do the little algebra, you see that this is just the sum of the square of this coefficient. So this coefficient, in fact, is the probability at any time for the particle to be in the quantum state defined by this psi n, or if you, this is a more popular notation, this denotes the quantum state n, and depending on the spectrum of the operator, suppose it's discrete, you have an infinity of them. Typical case is the harmonic oscillator. Okay, this is the ground state, the least energy states, and as you heat up or you shake the system, you excite higher and higher states, and these are described by higher order polynomials. But that's not a course of quantum mechanics. The point I want to make is that there is an inherent parallel content into the Schrödinger-Bessel. Already started. Let me take it out. It's still silent, but and this I'm sure they want me to change the gas bill and this kind of thing, right? And we don't want. No, the point is that you have suppose you have the system in an highly excited state, there will be many of these coefficients which are substantial. And each of them, if you wish, carries information. And each of them can, in a way, process information and totally independently of each other, because as you see, we do a linear superposition. Linear is a magic word. Quantum mechanics is linear. The Schrödinger equation is linear. You can fully cache on the superposition principle. This is key for quantum computing, because in fact, you have the same system. It can be simultaneously, there is a probability to be in different states. And these states are basically independent of each other. So in principle, you have a virtual infinite potential for parallel computing, because each of the states stores information and can process information, okay? And in fact, we can be more precise, but again, keep going with the basics of quantum mechanics in the wave function representation in Schrödinger. You can think of this n-dimensional space, Hilbert space. Of course, here for obvious limitation, I represent it in the plane. This is the equation. I don't spell it out, but there is basically a Laplacian term, which is the kinetic energy, and the potential energy term. In Hilbert space, since this is the imaginary unit, you have basically the fact that this evolution, you just start with a wave function at a given time 0, and it's basically a rotation, because the so-called propagator, which moves the initial state into the actual state, is x minus AHT. H is emission, you can show that. And so AIHT is a unitary, meaning that the wave function in this n-dimensional or principal infinite dimensional space is rotating, but it stays on the surface of a unit sphere in Hilbert space. Okay? This is called unitary evolution, and this is a constraint. It means that if you take, and here, of course, I forgot to integrate in space, which is what this bracket means. So you take psi star psi, which is the probability, you integrate over all space coordinates, and at each and every given time, this quantity is supposed to be 1 and never depart from 1. This is called unitarity. Incidentally, quantum mechanics is also conservative, and it means that the energy is also conserved in time. So these are the basic constraints of quantum mechanics: unitary and Hamiltonian. Now comes the weird part of quantum mechanics, the one which is less familiar. And let's move to the essential brick of quantum computing, which, as you know, is the qubit, quantum bit. What is a quantum bit? Let's make reference now to the case where we have just two states, 0 and 1. Okay? So coming back, we have just a two-level quantum system where you have the ground state and the nexus state. All the rest is decoupled. You forget it. Okay? So your quantum state will be described by 0 as the ground state, 1 is the first excited state, and there will be two complex coefficients which describe the wave function associated with this. Since they are complex, in principle, you need 4 numbers to describe this qubit. Okay, this is a qubit representation. But as a matter of fact, since you know that the norm of this wave vector has to be 1, and since the phase is actually is an arbitrary degree of freedom, which can always be scaled away, in fact, there are only 2 independent parameters in this representation, and these, in fact, are associated with the so-called block sphere. The block sphere is a sphere. You can think about a normal sphere where there are 2 angles, okay, theta and phi, and you can represent the qubit parametrically in terms of these 2 parameters. Now, how do you recover the standard bit? Conventionally, if you have the qubit, can be anywhere in your state. That's why the qubit represents actually an infinite amount of possible states. That's the power of the qubit. In fact, there will be a discrete in practice. Suppose you have n state, there will be 2 power n configuration associated to the qubit. And that's where you recover the exponential complexity I was referring before. And of course, the standard, the digital computing is just pole north, which is 0, ground state, and south pole is the first exciting state. My brain doesn't work this way. I would have put 0 here and 1 here, but that's the convention. That twists my brain, but that's how it is. The important point is that the quantum system moves the vector, the qubit, along on the surface of the block sphere, but here comes the trick. And when I learned that the first time, not long ago, it was kind of shocked. Because, oh, fantastic, we have a system qubit which represents exponential amount. There is a little tiny detail that when you measure, sooner or later you have to measure, right? If you want to extract something. When you measure, a weird thing happens that no matter where you are on the sphere, you end up either on the North Pole or in the South Pole. When you measure, the system becomes plastic, which is a bit of an embarrassment because you lose apparently all the power of the quantum computing because you lose the exponential advantage. Now, here I think you all agree that quantum physics is really weird because you may ask, okay, but how do I know whether I land on the North Pole or on the South Pole? And since I see young faces here, I would be tempted to ask questions as I do in my lecture. Am I allowed to do that? So some young voice, how do we know whether we land in 0 and 1? Any suggestion? You know the trick. You studied before. Yes. Indeed, it's totally right. The probability of landing in 0 is C0 squared. Okay? And likewise, C1 squared will be the probability of landing in 1. The thing is that when you do it in practice, what does it mean? It means that you have a quantum state, you measure once, and suppose I have 0.3 here and 0.7 here. It means that on average, it's like throwing a dice. 3 times, if I throw my dice 10 times, I expect 3 times 0 and 7 times 1, right? But I have to throw the dice 10 times, okay? So quantum computing is inherently probabilistic, just, I mean, for many reasons, but one basic reason is that you have a probabilistic representation of the state. And I'm very sorry, when you measure, you get back down to earth, okay? So that's something that, and okay, you all know about the Schrödinger cat. Is the cat alive? Is the cat dead? Nobody really, Feynman famously said, if you don't understand what it means that the cat is simultaneously dead and alive, don't worry because nobody understands. It's totally counterintuitive, and no, but that's serious. And up to 10 years ago, maybe 15, people thought that this was, when you are in the mood of killing some hours at the airport and nothing to do, then maybe you think about the cat. But the cat is real. Experimentally, they have shown that this effect really exists. Entanglement exists. And we'll come to that shortly. Meaning that the live cat is 1 and the dead cat is 0, but you don't know until you measure. Okay? That's very, very weird. It's totally counterintuitive, but I mean, the mathematics is consistent and the physics, the experiment tells you that. This is how quantum mechanics work. This is called the wave function collapse, open problem. Nobody really understands, because when I tell you that Schrödinger is linear, I'm hiding a very important fact, that when you measure, you are not linear at all, because you just project a single quantum state, and that's absolutely linear. But nobody really knows how to incorporate the measure process into the mathematical formulas. That's a fact. So when I tell you quantum mechanics is linear, caveat, it's linear until you measure, and sooner or later you have to measure. Another practical point, when you do quantum computing, one of the primary precautions that you don't want to measure things. You try to measure as least as possible, because as soon as you measure, you destroy your house of cards. House of cards is an expression that came to my mind, and I was very delighted when I saw it in a paper, which I recommended, which makes really a very nice point about this. Really think about an house of cards, and that house of cards is very, very, and when you measure, you destroy it. Okay, so having said this, another thing which I want to add at this point, because it's really basic, fundamental concept, if I want to reconstruct these quantum states, okay, and I have a system with q qubits, suppose I have, nowadays IBM can offer on the paper 433 qubits. It's a lot. I tell you that if you want to reconstruct this state, knowing where you were in the block sphere, the number of measures you have to make is of the order of 2 to q, which is a lot. So reconstructing the quantum state, which I will tell you later, is something that you may want to do, and we do that all the time when you do the classical computer, because it doesn't cost as much. In quantum computing, reconstructing the classical state after you measure is something you don't want to do because it's exponential. So now you already have some, feeling of the limitations. Okay, the entanglement, again, I don't have much to say. The entanglement is something which, as Feynman said, I mean, you really don't understand. You have Alice and Bob. I'm not an expert. This is more relevant, I would say, for quantum telecommunication. But the point, the way I see it, is just a sort of marriage that you can break. No divorce in quantum mechanics. If A and B are entangled, it means that if I do something on A, I will do something on B as well. Okay, and the two are just, and the important thing that it doesn't really matter where they are. They could be totally far apart, but they are part of a single entity, and you cannot break this entity. Meaning that if this is a photon with spin up, and I send one photon right, one photon left, far apart, then when I receive the photon right on that location, I flip the spin. At the other location, the other spin flips as well. Absolutely, totally weird. You think this is science fiction? No, that's what they measured. They did experiment, and that's exactly what it is. It's totally weird. It means that basically space does not. It doesn't. People, myself included, I thought, well, there must be some mechanism by which light signal propagates faster than light. No, it has nothing to do with signal propagation. It is faster than light in the sense that you flip here and you flip there, and the flip here comes in a time which would not be, which is far beyond the possibility of light speed, but that's what they measure. Fact, experiment. So entanglement exists. Mathematically, it's easy. You take two states, A and B, and you know that if they are the direct product of each other, there is no entanglement, easy. And if they are not, I think I need to spend much time here. I have A0, 1, B, B0, B1, then I generate A direct product of AB. It means that the coefficients are the direct product of A and B, and if they are not, you say that the state is tangled. But that's not, I don't want to spend much time on this, except for saying that, and this is key, this entanglement, which is crucial in quantum computing, it's extremely fragile. It is house of cards. There are two basic manifestations of the fact that this quantum system any quantum system interacts with the environment. Classical systems do the same. But quantum system and the entanglement is particularly sensitive to perturbation. We were discussing with Alfio this morning. Our standard computer also are sensitive to, say, cosmic neutrino, could flip a bit from 0 to 1 just by accident. And that, however, happens with a it's a very, very rare event. If I'm not mistaken, the circuits in a classical computer, there is such an event, the probability is 10 to minus 18. And there are circuitry in our computers, digital computers, which correct for this. Okay. But since the error is a very rare event, the circuitry is, it's relatively small. Quantum systems, in particular entanglement, have an error rate which is 1%, 1 per 1,000. It's enormous. So the noise, the quantum noise, is overwhelming. And in the early days, people thought about decoherence because the entanglement itself can crash and then the qubit is empty. But here the technology has made improvements. Now they can keep the entanglement alive up to almost a millisecond. After that, the entanglement is gone, but during that millisecond, you can compute. More seriously, even more serious than the coherence, is the fact that even if the qubit is alive and well, you can still move the quantum state to the wrong location in the Bloch field. So it's entangled, but it doesn't land where it should, okay? And so this is called quantum noise. And, well, I can directly go, this was really funny to me. This is what you see. We had an agreement with IBM and CERN to access the real quantum hardware here from IBM. It's not for free, I have to pay. And this, I was amazed when I saw that each of these qubits, basically, comes with his own readout error. So each of them has a certain error, and somewhere you see it, the scale, huh? It's percent. When I saw that, I said, well, this cannot be true. I mean, how could you possibly compute with a system which is floating in the noise? Well, you can, but it's an hard job because essentially, and here I give another practical point. When you read big claims, which I understand, the sermon, we are recorded, but I think I can say that. When you, no, it's fair. When you hear the chairman of IBM, and it makes sense, this position, saying we have now 433 qubits, that's absolutely very, very remarkable technological achievement. The question is, how much of these qubits can I really effectively use after I've taken into account the quantum? And I tell you that the number of effective qubits is much lower because of this. There is an enormous amount of work on it. No, but it's IIT. So I think that your channel is very effective in this case. So they already know that. No, I'm not trashing IBM at all. I'm grateful to IBM because I promised using these computers was fun and very, very useful. So we paid money for that, but it's well spent money. But it's amazing to realize how much the noise is affecting the real, I mean, the facts. The fact is that we had ourselves 127 qubits, okay? And I come later, you could do a lot with it. But as a matter of fact, you can, because of this problem, you can effectively use maybe 1/10. There is nothing wrong with that. I mean, that's beautiful, that's challenging. But all I want to say that when you read the nominal qubits, which is a big achievement, okay, as a scientist, you have to ask yourself, okay, how many of these nominal qubits can I really use in my application? That's a serious question. That's all I'm saying, okay? So I'm not trashing anything.
Where is this computer? Are you using?
This is a Russian, Zurich. IBM.
No, where is it? Oh, in Zurich?
Zurich.
Oh, it's in Zurich.
Yeah. I mean, you know Ivano Tavernelli. Yeah, Ivan is a great guy. No, this is I thought myself it was in your town. No, it's in Sweden. As far as I know, I never touched the computer, but they are in. So there is a huge technological challenge, and the technological challenge is twofold. On the one side, when I tell you that you have to correct or mitigate, there is error mitigation, it means that there are people studying how you can possibly keep this noise as low as possible, or even better, take advantage. Monte Carlo. I mean, there are many beautiful directions for the young generation here to go. Fascinating. Even in the end, it might fail. Who cares? It's bad. But there is a technological challenge because, as I told you, the quantum noise is orders of magnitude larger than the classical noise. And that's a technological challenge. And I think here the experimental quantum physicists are really doing a great job in, there are several physical implementations of this. Could be superconductors like IBM, could be ion traps. There are 3 or 4 different physical implementations. But the bottom line is that the quantum noise is far, far larger than the classical one, and that's a huge challenge. Again, just to give a practical idea, when I say that this is the real thing, and it is, what I mean is that inside these quantum computers, you have quantum gates, and this is a beautiful result of theoretical computer science. You can show that you can do universal quantum computation with a few fundamental gates. For those of you who have seen the Pauli matrix in quantum mechanics, they're basically spin flipper. We are fully into linear algebra, nothing else but linear. Okay? And if your problem, if your Hamiltonian maps one-to-one with these gates, champagne, because clearly you have a one-to-one relation between your mathematical model, your algorithm, and the algorithm. And that's the case where you can expect the so-called quantum advantage. But not all problems are like this, and that's the difficult part. So in the end, the assignment is 3 basic steps, which each of them are double somehow. But first of all, you have to mathematically, you have to design your quantum algorithm. And as far as my experience goes, you have really to take your brain and deposit elsewhere and start thinking differently. Really, I mean, I can offer this as a first-hand experience. As Alf, you have some amount of time on my back of high-performance computing with digitals. And I promise that when I had to do that, I really to think differently. And again, Feynman at some point says, think different, right? I think they have this in mind. Then when you have designed a quantum algorithm, which is itself task and so on, you have to estimate its computational efficiency, because the fact that it is quantum doesn't mean that it is more efficient by default. And I'm not talking the noise, I'm talking the number of operations to do. Then, and this is something I would say that you don't find very frequently in the papers, many papers just stop there, say, oh, I have an algorithm, fine, and that typical move, and then you emulate the algorithm on a classical computer, which is interesting, but that's not the full job. Full job is to write down the quantum circuit, map your algorithm into operations, which in turn map to the quantum gates. And IBM has a great software called Qiskit, it's a sort of compilator, which does the job for you. You provide the algorithm, and Qiskit would tell you, this is the best circuit for my class, which is a big help. Okay? But then you have to estimate the noise effect, because clearly, if suppose your circuit is made of 100 or say 1,000 circuits, 1,000 gates, each time you go from one gate to another, the noise gets multiplied. So a typical problem is the circuit depth. How deep is my circuit? If the circuit is, say, depth 10, you are fine. If depth 100, you have to fight against the noise. If it's above 1,000, it's basically unviable. And I might be wrong, but my perception is that this step 2 is rarely taken in the literature. You read papers, quantum computing for fluids, and you realize that they stop here. Okay. And, or better said, they design the quantum algorithm, they estimate the computation complexity, and then they jump here, which is not the full job. Sometimes they jump here because you cannot simulate on a quantum computer, but I think part 2A and 2B are the things which I see mostly missing in the literature. Then I take the blame for this statement, but at least for the papers I've been looking at, namely quantum for fluids, that was the case. Best candidates, I think, I mean, I'm really not an expert. I only know my own corner, if you wish. But I think in the quantum many-body, quantum chemistry, quantum materials, there might be some real results in the next decade. Real results mean it's called quantum advantage, meaning that you can do something that no classical computer could do. I think here there is a reasonable hope that something like this will happen in the next decade. For fluids, I'm afraid we have to wait a bit longer. So at this point, part 1 is over, so I think it's probably the most important one. So if you have any questions, I would be very happy. We don't need to cover all the material. Part of it is very specialistic. Not sure I want to present. Any questions? Okay. So if there are no questions, then we move back to a more familiar ground in fluids. I assume most of you are including the youngest in the audience, know that fluids are complicated. Fluids are old story, right? Some people, many people, I would say, mostly, well, many people think that this is an old science because these equations, the Navier-Stokes equation, are fully classical, and it's basically Newton equation written for a finite volume fluid, and they are known for more than 200 years. So what boring, right? Fact is that it is not really, I mean, it is the equation which makes science, but more than the equation itself is the solution. And solving this equation, as you know very well, in this place, it's a tough job, right? I would say there is a ceaseless demand of better algorithms to solve the equation of fluid. And so and you might or might not know that the complexity of the Reynolds number, as you know, is a measure of the nonlinear strength or the nonlinear interactions versus dissipation. And this number is basically gives you the strength of nonlinearity versus linearity. And the fact is that for ordinary objects, take a car, of course, car is a piece of very sophisticated technology, but it's something that we have under our eyes daily. A standard car would have Reynolds 10 million, meaning that fluid dynamics is very nonlinear. Right? And as a result, if CC is computation complexity at 10 to 7, it means that I can expect, and there is at least a factor 1,000 in front, but I have to expect of the order of 10 to 20, 21 operation to solve, do a fluid simulation of a car. And even if you have an EXA computer, which means 10 to 18, 10 to 24 means 10 to 6 seconds, which is about 10 days. So the car, I would say, is on the verge of what we can do with exascale computing. Now let's go to weather forecasting or astrophysics, cosmophysics. No way you can do a full detailed simulation using classical computing. So that's why there is always demand for better fluid dynamic algorithm. And I mean, in this place, of course, you have contributed greatly to that. Now, this picture, what I was saying before, what can we do with a quantum computer for fluid dynamics? And if you look at this picture, it looks like more than a dream, actually. In fact, it's a nightmare because it would mean that, I'll tell you in a moment, that fluid dynamics would be dead because we would know everything. Look, this is real data. This is IBM. And this is true. Osprey today offers 433 qubits. question. What can I do with 453 qubits? Answer, easy. This we can do on the back of the envelope. The number of operations needed to solve a fluid at Reynolds RE is Reynolds Q. How many qubits do I need to represent this dynamic state? 2 power q. You do the algebra, and it's 3 logarithm base 2, which is basically 10 logarithms. A very simple form. It means that if I have a car, Reynolds is 10 to 7, log 10 is 7, so with 70 qubits, in principle, if I could use these qubits, forget about the noise, blue sky scenario, and you don't even see that, it's here. So I can, this is where the exascale, okay? Our largest electronic computer just squeezed down in this little corner. Ideal life. With this guy, I can do, you see, 403 means that I can do basically Reynolds 10 to power 43, which I think the entire Earth is probably, I want to say, I think it's 10 to 13, 10 to 14. So here you have already by far simulated, assuming you have the data, blah, blah, blah. I'm putting things very simply, but in raw calculation, here is far more than you need to simulate air circulation around the entire. So it's fantastic, it's unbelievable. And we really need to go there? For the moment, I see no use. Unfortunately, so the potential is fantastic. It's incredible, but realizing this potential is very hard. I told you about quantum noise. Now, on top of all I've been saying so far, we have to add 2 elephants in the quantum computing room, because quantum mechanics, I told you, is linear and it is conservative. In general, fluid dynamics is neither. For sure, it's strongly nonlinear, and incidentally, it's also non-unity because fluids dissipate. So there is a very basic difference between classical fluid dynamics and quantum mechanics, and the question is, how can we handle these additional problems? And honestly, the answer is that we don't know. I mean, there are many ideas around, including ours, but no, the problem is entirely open. There are many issues associated with nonlinearity, but one which always strikes is that you cannot do x times x. Okay, you have a nonlinearity, you have u squared. Say in a classical computer, you do u times u. No, you cannot do that, because you know there is this famous no cloning theorem. If you copy x into another, you cannot have 2 copies of the same quantity, because by the time you copy the first into the second, the first is gone because of the, it's like the measurement problem. You can copy one classical state, but not the full quantity. So you cannot do x by x, just to give an example. And you cannot, when you do time stepping, you compute the next state, and then you copy the next state and the actual state to do the next step. You cannot do that here. So that's why I'm saying you have really to think. And dissipation has its fair share of problems, but nonlinearity is more. Now I get somehow technical. Here we are. MOX, I think you deserve more than just general. So I'm telling, I don't know how much time I have, but I can cut it anytime. Let me tell you how we try to go around the nonlinearity problem. There are several strategies, but I don't think there is time to. So let me tell you a little bit about this Carleman-Koopman quantum. Okay, so very quick. Carleman is a trick to turn any nonlinear equation into a linear one, but in infinite dimension, price dependent. And the idea is very simple. Take the logistic equation like this, is f minus r f squared. R is a nonlinearity parameter. You know the exact solution, of course, but in Carleman, you would call f squared, you call it f2, and this formula is linear, right? F is f1, f squared is f2. And then I have to write an equation of f squared. In this case, it's trivial, and you end up with the hierarchy. And you say, okay, at some point, I truncate the hierarchy, and I will have a solution which is hopefully good enough in terms of approximation. When you do the same, this is too sophisticated with Navier-Stokes, I don't need to convince you that things are significantly more tangled, right? And you generate, this would be the nonlinearity in Navier-Stokes. A and B are the Latin index XYZ, and this is the way of writing the divergence. But I mean, forget about the detail. The important point is that when I write an equation for UU, I generate UUU, and there is worse than that. There are correlations between flux and pressure, and it's complicated. And I think this is a beautiful problem in mathematics because I think nobody knows, and there is a combination of two errors, the truncation error and the discretization. And that's what we are doing these days, but I think it would be very important to have a serious numerical analysis of the Carleman truncation as applied to Navier-Stokes equation. What we did is something different. Let me skip. But just to give you an idea, people have done that and they've solved the Burger's equation. Okay. Solved means on a classical computer. They give the algorithm and then they write the algorithm on mathematical or MATLAB or whatever. Okay. But even then, they solved these, I think, if I remember correctly, 16 grid points, 4,000. This is basically where you are with quantum computing today, okay? And not even, because this is emulated, okay? But the algorithm is there. And steps in time. And interesting, they have a theorem saying that if Reynolds exceeds square root of 2, the algorithm cannot converge. They run it, and it does till Reynolds 40. There is a problem with the theorem. But it's beautiful. It's really beautiful math. Okay, that's so. Again, I'm now rushing. We have a different way of setting things, as Lars was mentioning. I spent basically most of my life, scientific life, dealing with the Lattice Boltzmann. Lattice Boltzmann is a beautiful way of representing fluid equation with the different mechanisms. Let me try to convey the spirit in one sentence. The big point of Lattice Boltzmann is that instead of moving information along the material lines where the fluid moves, which is complicated, in Lattice Boltzmann, you move information along straight lines. These are like discrete velocity, discrete strain lines. There are many of them, but the information, no matter how complex the fluid, always move along a straight line. Meaning that from time t, the guy who moves right, and it's here at time t plus 1 goes to the next lattice side, and nothing is lost in it. Zero round-off. This is exact from the computation point. And this property is just at the core of the success of the lattice. And our hope was that these properties, which really are the basis of the success of Lattice Boltzmann for classical fluids, maybe they could be used for quantum computing as well. But there is one point which is easy to convey, if you believe me, about Lattice Boltzmann. The second point about Lattice Boltzmann is that this quantity here, the local equilibrium, contains the velocity square. So the nonlinearity is here. But unlike fluid dynamics, where you have u grad u, which is non-local and quadratic at the same time, this guy is u squared, and it is local. This operation you do side by side independent. That means that formally, the nonlinearity, mathematically speaking, is u squared versus u, and this is called Mach number. So the hunch will be that due to the formalism, and I still don't believe that because the physics is the same, but the mathematical package is very different. And one difference that for classical fluid really didn't matter much, but here might be very important, is that the nonlinearity is measured by Mach instead of range. And Mach is, for a car, is 0.3, not 10 to 7. So this was pointed out by a group, I'm talking a few months ago, and they did a benchmark on the 32 squares, so the grid is still small, because when you do the Carleman, you generate a lot of that. UU generates UUU, and this is an combinatorial explosion of variables. So you cannot even emulate after a while unless you stop Carleman very, very quickly. Here they stop Carleman at the third level, and this is the error between the solution of the Navier-Stokes equation and Navier-Stokes Carleman equations, level 3, and as you can see, the convergence is pretty good, 10 to minus 4. So the Mach argument seems to apply. This could be a big thing, because if the nonlinearity is measured by Mach instead of Reynolds, it's huge. I cannot believe that is too good to be true. But nevertheless, so we did the same. I will spare you all the hard math. We did a sort of Kolmogorov flow and basically same result. We stopped Carleman, that's level 2. These are two different implementations, never mind. But again, we are in the order of 10 to minus 4 with Reynolds number, which are in the order of, let's say 10 to 100. Okay? Sorry? 10 to 100. I say like 100. And I mean, of course, don't quote me, but if I could, and I can, extrapolate, it will look like the error is scaling like the square root of range. We don't know. And the number of time steps is still very small. So we cannot draw any conclusions, but there is an indication that this Mach versus Reynolds argument might be, I cannot believe it completely, but might have something. Unfortunately, and I'm coming to the end, I spare you all the details, Claudio really did an excellent work. He wrote down the Carleman matrix for the Lattice Boltzmann. And I'm sorry, there is no way we could map this matrix, we can really run back into, we go back to the really basic, to these guys. Looks like this matrix, if I do a spectral projection of the matrix, I can represent in the metric space, it looks like this matrix is projecting over all these gates in tensorial combination of these gates, and there is no lower order truncation. The result is, in a way, terrible. Let me give you. When Claudio told me on the phone, I said, if I could, I would fire you because you're making jokes on me. He told me, Sauro, with one grid point, that's what he told me. With one grid point, the depth of the series is 200. He said, no. Alas, he is right. So I give you the bottom line, and that's where we are. So I'm really open to any kind of suggestion and collaboration. Lattice Boltzmann works like a charm. Mathematically, we converge second level Carleman, can you believe? Error type match. The mathematical hardness is perfect. But when we go to the real thing, design the circuit and see the depth, that's where we are. So now we are taking steps back and say, what happens with Navier-Stokes? Why? Because Navier-Stokes, I'm sorry, you may notice that this is a real thing in 3D. In 3D, if you have an incompressible fluid, you have 3 velocity components, basically. Okay? Here we have 19. There are many, but they are very convenient because exact streaming, blah, blah, blah. But they are 19. And when I do Carleman, 19 becomes 19 squared instead of 3 squared. Plus, there is another mechanism, which I will spare you, unless you're really interested. Not only you grow in the Carleman hierarchy with the number of variables per grid points, but also the number of grid points. If you go to second Carleman, you have 1,000 grid points. At the second level, they become 1 million, which is unbearable. It's like this one. So the hope is that with Navier-Stokes, since we have many variables, the depth problem might be much, much less vexing. But so far, we have not been able to converge. So you see, we might be between, as they say, the wall and our place, because Lattice Boltzmann is a charm, but fantastic. But we end up with an horrible depth problem. Navier-Stokes might have much of a less depth problem, but we don't know if it converges or not. First, because it's hard to control the numerical errors of the truncation error. And second, because the Reynolds argument might be true. And if the Reynolds argument is true, I'm sure that Navier-Stokes will do much, much worse job versus Carleman. And honestly, that's where we are. So I think, as I was saying, this is a beautiful topic, but we are at the point where we really need to talk to people like you, because, I mean, we need to know what Carleman from Navier-Stokes does. And so that's where we are. What, oh no, I'm going the other way around. And of course, there are possible, I mean, Carleman is not the only way to go, but that's the one we chose, and other people around the world. I'm talking, there might be maybe 20 people working Lattice on quantum computing for fluids, and more working on quantum computing for nonlinear PDEs, which is much more general talk. So in the end, I would say, first of all, for now, if you're talking quantum versus exascale, there is no question that exascale computing can sleep tight. I mean, really no threaten. But at the same time, I would say even if quantum computing for fluids would fail, and it's quite possible, we are really learning a lot. We are asking a lot of questions on basic quantum mechanics, and also, I would say, on numerical mathematics that we would never, ever, at least myself, thought about unless we had to solve this problem of trying to see what happens when you try to solve fluids on a quantum computer. So in my view, even if we fail, there will be a lot to learn. We are already learning a lot. So it's certainly a very, very worth enterprise. And given the mind-boggling potential I gave you, if somebody tomorrow comes with a big algorithmic idea or a big technological advance, I mean, as you saw, I mean, the potential is just. So I think it's worth at least trying for another few years. But we need more critical. So with that, I would close. I spare you the detail, but I hope I gave you some of the bottom line of where we stand and what the prospects are. So I thank you for your attention.
Thank you very much. Fascinating and challenging questions. So maybe I start. Well, I start from the Boltzmann stuff. If I understand correctly, when you use Boltzmann to solve Navier-Stokes, basically, you do not have the immediate interpretable equivalent of viscosity, right? But you can establish a relationship between what is Mach in Boltzmann and what was the viscosity in Navier-Stokes. Is it correct?
Well, actually, I don't have the slide here. In fact, after what we do, generally, this becomes a single parameter. We say relaxation of the distribution to the local equilibrium. And this parameter specifies the viscosity uniquely. So we do know what the viscosity is.
Okay. And how do you compute it? Does it come from your derivation?
No, this is an input parameter.
Oh, it's an input parameter.
So the viscosity is perfect. We don't need to. There are no ambiguities in that.
Oh, I see. But what is driving is the Mach number. And this is where you have the potential.
The point is, again, the point is this is the exact streaming, right? So this is the equivalent, if you wish, of the advection, except that the advection does not take place along material lines, but it takes place along.
Sure.
So that is exact. This is a memory shift, no floating point. Here I didn't write, but look here, rho u, when I have the distribution function, I just compute the average of the distribution function with each with its own velocity. So this gives me the momentum of the fluid at each lattice side. With this quantity, I go into the local equilibrium, and the nonlinearity is u squared. But it is local. This is computed at site r times t, so each site is processed independently.
So in particular, it's intrinsically parallel.
It's intrinsically parallel, exactly. But in this case, if you, as a mathematician, you look at this equation, say, where is the nonlinear parameter? It is u squared versus u, okay? Whereas, I don't know, it looks like a little bit like cheating, but in Navier-Stokes, it's different because in Navier-Stokes, you have an explicit representation of the dissipation, which is the Laplace. Yes. Right? I didn't even write it. Yeah, but you know what I mean.
Yeah, but we know that. Yeah.
Now, this is again in Lattice Boltzmann. You never dissipation is an emergent property. You never need second order.
So you get it a posteriori.
I get. We get it. Yeah, exactly. We know what the viscosity is, and dissipation comes from the relaxation to local equilibrium, which is a local process. Okay, and this is local. In this local equilibrium, the nonlinearity is u squared versus u. You never have u over u grad u versus me Laplace view.
Yeah.
It's formal, so I don't know how.
So this also explains the efficiency of Lattice Boltzmann with respect to the classical.
Oh yeah. In the classical framework, the free stream in MA they are key. They are the key ingredient of that. In the quantum, I never thought really about Mach versus Reynolds until these people brought up the point. And my reaction was, come on, give me a break. It's the same physics. But, you know, the mathematics matter, right? So it could be that the algorithm has a totally different performance. And honestly, Alfio, I mean, Claudio could get the Lattice Boltzmann working in 1 week. The guy is good, but first shot. Lattice Boltzmann is already struggling for 4 weeks. Also because, in Lattice Boltzmann, the algorithm is given, we have no discussion. In Navier-Stokes, how do we discretize? Well, we took Euler with center finite difference, which we know is unstable in principle, just to give it a try. Maybe the answer depends on how I discretize the Navier-Stokes.
So in particular, when you made the comparison, you say that given time that there is an analogy between, or say corresponds between, you compare the result, the error, right? The difference between the solution of Boltzmann and the other one.
Very fast.
So can you say in that case how many grid points you use for Navier-Stokes and how many?
Okay.
How do you establish this comparison? This one, precisely.
Okay. So what we do, let me do it with Lattice Boltzmann because it's more. So what we do is the following. This is basically Lattice Boltzmann native. So I solve this equation, I have it all, but I have a nonlinearity. Okay. FF. Okay. When you construct the Carleman, you have Fij is Fi times Fj, and you have these quantities which are third order, even though it's written like this, and this is fourth order. Okay. So this is what I call Carleman level 2, because I'm generating a dynamic equation for the quadratic. And there are terms, this is cubic, I know for sure, and this is order 2, 3, and 4. So some of them I throw out. Then I compare the solution of these alone, this solution, with the solution of this equation where this I call Fjk, and for Fjk, I solve an equation which I truncate. So I'm making a mistake, for sure. What I'm telling you is that if I do this on a 32 by 32 grid, truncate order 2, which is the least, I get the two solutions are on top of each other up to 10 to minus 4.
Yeah, but in Navier-Stokes, you have an idea of how many grid points used?
It would be the same. But in Navier-Stokes, we are not able to converge. That's where we are. After about 1 month, we still do not have a case where, with non-zero Reynolds, where the Carleman would return a reasonable result. Is it a bug in the code? Is it because it is true that with Navier-Stokes, Carleman does not converge? That's why I would need, if one applied mathematician would come and do the clean job and show, look, Carleman with Navier-Stokes, forget it. Could well be. We don't know. And, I have one postdoc.
Well, what I can say is it's not very important, but when you use classical, classical approach for Navier-Stokes, you never use Carleman. You use other linearization techniques.
Yeah.
Which is not the proof of anything, but it's just.
No, but that would be, as I told you, I had this question immediately 2 years ago to a big guy in quantum computing, but not fluids. And he told me that you cannot do iterations. This is the general problem. Whenever you do, it's just like doing time step. It is this copy problem. If you copy the previous iteration, the new one, you destroy. And so he told me, no, you cannot do that. But you're right. We took the Carleman way, but there are other possibilities. I don't see much of a chance over there. But I would like to know whether what Carleman does on Navier. This, forget about quantum computing. This would be very valuable information. Because maybe it does not convert that. It's just more
questions. Other questions? Yeah.
A curiosity, and thanks first of all for a wonderful lecture. I'm curious about this issue you mentioned related to Reynolds scaling and Mach scaling. I wonder if what happens if you consider Euler equation instead of Navier-Stokes equation in a, let's say, in a
I don't know. I don't know. Because your point would be the Euler would be virtually Reynolds infinity. I don't know. That's a good, very good point. I'm just thinking, I don't know. I have not seen this question asked. Should it better or should it be worse?
No idea.
Is that true? I don't know. You tell me. There is more demand on Navier-Stokes than Euler on the fluid community, or I mean, I know the Euler is the famous problem. You know what happens at Reynolds infinity. The clay.
Orienting shuttle.
Yeah.
And, so the idea was to have Boltzmann and then Euler and then Einstein. So
yes.
The three approaches were actually.
No, but the question is interesting. Yeah, yeah. I'm thinking loud. But Euler would have the advantage that it is, in fact, conservative. Yeah. But I've not mentioned the problem that we have because of dissipation. They are not as, I would say, profound. But dissipation also is bothering if you do absolute quantum computing. I mean, it's really technical stuff, but believe me that. So Euler would not have this complication. But as far as the nonlinearity is concerned, I think we are more or less in the same baskets.
It's just a curiosity in quantum computing. Since I know practically little about the things that I read sometimes. If the results are probabilistic, how eventually you get the final solution? You run several times and then you make averages.
It's called circuit shots.
Okay.
Sometimes you read in the paper, we have done 1,000 circuit shots. It's just like ensemble average.
Yeah, ensemble averaging. Okay.
That's also.
This is Luca. So what? Okay. Okay. Any further question? No, I'm also one. It's a bit aside, but and please correct me where I'm wrong. I had a few years ago, some 10 or 20 years ago, I had a student in Lausanne was interested in using Lattice Boltzmann, and
actually, I think I got the paper of yours.
Okay,
it must be that.
But this is the only exam. Then we stopped, and at that time we tried to, because the idea was that Lattice Boltzmann is extremely effective when you have somehow simple geometries. This was the idea that we had at that time. So we are trying to solve the problem in hemodynamics and try to use Lattice Boltzmann in a cylinder that was fully included in an artery, and then using finite elements near the wall, and we face the issue of coupling Lattice Boltzmann with the quantum. So more generally, is there a simple or natural way to find corresponding variables to match when you move from Lattice Boltzmann to classical fluid mechanics?
So, okay, well, let me answer this way. First of all, the way people do, let me go back because I think I have a picture in this. The way we do complex geometry is like, I mean, complex geometry is one of the assets of, this is a Lattice Boltzmann configuration.
Oh, wow.
But typically you do that in companies.
You do that?
This was a private company.
Okay.
Which is now actually was in Boston, and it was acquired by Dassault 6 or 7 years ago. And they do use it for commercial purposes. The way you do, at least I was working with them 20 years, but by now 10 years, I don't know exactly what they do, but in those days, I think they still do the same. This is Cartesian. Since the method is so effective, it is that they put in.
You can overkill it.
Those days, you would just do staircase. Right? And you typically, where a finite element code would use those days maybe 10 million nodes, you would put 100 million.
And the boundary term, boundary conditions?
The boundary term is amazing. Last time I was there, I'm talking about 10 years ago with this company, they showed me they had the patents, right, of the boundary algorithm. It was a paper that thick, and you could find in few words, every 10 pages of equation.
Oh my God.
Totally impenetrable.
Okay.
But each time I visited, they were struggling again.
So it's a kind of cuisine done for handling the.
Boundary condition with turbulence in complex geometry is honestly, it's an act. But I mean, so the point is dealing with complex geometry is one of the points. Well, we do Cartesian all the way, period. Now, how you combine with some finite elements, we did many, many years ago, a finite volume formulation of Lattice Boltzmann. And honestly, we lose the advantage of the exact scheme. So at that point, honestly, I don't see much of a point.
The advantage is not that evident.
So but what you say is correct. I mean, I have no experience myself. I think the cross-talking between finite elements and Lattice Boltzmann should not be. I mean, it's boring because you have to be careful, but conceptually, I don't see much of a problem. But I have never. My point is, to me, but it's my personal opinion, Lattice Boltzmann is good as long as you can keep it simple.
Yep.
And simple means just Cartesian grid. There you go.
Very good. Is there any question or comment from remote? You are very remote.
You mentioned the fact that stepping is not possible. What about time-dependent problem?
Yeah. I mean, again, I remember that when I was first educating myself, I said blah blah blah, and this for one time. What is this? Two things. My reaction was, okay, maybe they have a sort of implicit method. You know, you look just for steady state and you do one big jump, and sometimes you end into the steady state. I don't think that was what they mean. You can do one long time step, okay, and how would I say? If you do, for instance, if you have the scheme, explicit scheme for t from t plus 1, you can write the same scheme from t to t plus 2, right? And you have the square of the operator. So if you do that for 10 time steps, you have the thicker operator, but in one jump, you go from 1 to 10, and you don't lose accuracy, but of course your algorithm is much less sparse. You do what, I mean, as I say, each time you measure, you're killed. That's
you have to compute in one shot.
Again, if there are computer scientists here in the audience, I don't know. I mean, there is a theorem, upper bound, though, that to reconstruct a quantum state with q qubit or n qubits, the complexity upper bound is 4 power n, which is horrible. It's not 2 power n, it's 2 power n squared. And that kills you, but it's an upper bound. So maybe there are tricks, algorithmic tricks, to kill this barrier. That would be a huge result. Maybe it's impossible, but who knows? But I mean, time stepping and iterations are really basically, you try to stay away as much because of this cloning story. You cannot copy. When you copy, you lose just recover one possible state out of exponential and so on.
Many thanks for the amazing talk. I have a question on the algebraic structure that you showed at the end, that is definitely not sparse and definitely not row rank in the basis that you have of the computing. My point is, I'm trying to wrap my mind if it is due to the equation that you are solving or to the Carleman technique that you use. So if one would use like the Lattice Boltzmann linearized in some other way so that you don't have it, so basically you have Stokes at the end or something, is the structure of the matrix still as complicated or not?
I don't know, but that's exactly the question you're asking. For sure, the structure of the matrix depends heavily on the scheme you use, and I would say maybe, I mean, not the scheme, on the representation. Representation is why, I think. Well, it doesn't matter after. So representation means Navier-Stokes versus Boltzmann. These are two different mathematical. Okay. Grazie. Grazie. Sì, Gracias. So this to me is a representation. This is a physical fluid, is a standard representation, and I call it Navier step. Okay, everybody knows it, fine. And there you can choose. You have an option of different discretization schemes. Okay, the Carleman matrix will depend. Given this representation, a Carleman matrix will definitely depend on the discretization scheme you choose, and it will be anyway large, but it certainly depends. Now with Lattice Boltzmann. No, I'm going back. Should be because it's okay. With Lattice Boltzmann is a different representation. This one, and you would not even recognize the digital dynamics, right? For I think 10 years, I was back then. I would go around, not 10 years, but at least 5, 6 years. People say, "What is this? You are showing things. Please give us a break." And then you show the results, and they say. But it took a long, long while. And in perfect good faith, people would not. I mean, come on. You go to a mechanical engineering department and say, this is the query. I mean, you sympathize with people who just don't trust them, right? So this is a different representation. Now I tell you, this I cannot show. But again, mathematically, when I write down the equation for the higher order Carlemans, they are a piece of cake in mathematical sense because all the beautiful properties of Lattice Boltzmann are preserved. And I mean, I did not expect this work at the first shot. Okay? And here there is not much of a choice because this is the algorithm. It's not that I have to choose whether I do center finite differences or, you know, upwind, you give me your best. It will certainly depend on these details, although I don't think it will change much, but we don't know. Now, there is a very unfortunate property which I only recently realized. I skipped it before, but now let me come back. The great beauty of Lattice Boltzmann that the right movers move right without thinking. They come from cellular thought. Don't think. They are programmed to move right. And they land on the lattice, which, as you know, means that you have no artificial dispersion. You have a lot of good properties. When you have, it's just like having upwind. It's a directional upwind, right? That you can do because you move along straight. And this is an enormous advantage. But here it maybe just turns back on you. Suppose you have and just revert the arrows. Okay, I start with this 1, 2, 1, and 2 at the same lattice side. Or go back in time. If I have this non-local distribution, this is sort of tangle. This is non-local correlation. At the next time step, this non-local pair will be here, and after 2 time step, it will be here, which means that if I start with this, after 2 time steps, I'm here, and I have to fill the entire lattice, which is a disaster. Apparently, in Navier-Stokes, you don't have this problem because you are sitting, it's just like Euler versus Lagrange. So it looks like this property of the direction is the key of Lattice Boltzmann classically, is the key of success. Here it looks like it's just hurting you very, very happy. I was not happy to go back to Navier. I've done the reverse process for 30 years. But you know, you have to be open. As we stand, and Claudio pointed this out to me. I didn't believe him first. Said, come on, that cannot be. But just because, you know, it's non-local, because if I'm a right mover, I move to a different side with respect to the left mover. And in Navier-Stokes, we don't do that. Every component stays where it is and moves in time, period. It's much more local. But I am afraid it does not converge because of the range. So you should tell me, guys. No, it's important. It's important because the depth problem will be much less vexed. It's not an academic question in the academic questions are good in my view, but in the sense that it's not just formal. It's substantial. If you could lower the depth by orders of magnitude, that would be important, very important. And then there is your idea. I don't know. I never thought again about the idea of just doing linearization, but we have the problem of copying the information from one iteration to another. Of course, that was my first reaction. Why don't we do that? And then they told me, no, you cannot because pseudo is the same. But they have the same problem in everything. I talk to people who do quantum mechanics, they do iterative procedure, they cannot do it.
Very good. So I think we can stop here. And for thanking our speaker again, let me remind you that there is a coffee at the 6th floor right now. Thank you very much. Sauro, great. Very nice.